So this is a potential problem. The question is the following, and this is from worksheet number 5. This is problem 1. So consider a long wire of length L with charge plus Q. A cylindrical conducting shell of inner radius A and outer radius B encloses the wire. The shell carries a charge of plus Q. This figure here is a 2D face cut, so you can imagine this goes infinitely in and out of the page. Assume now that A and B are much less than L, then in this case, Gauss's law gives us the following electric field. The problem is the following. First, what is the potential everywhere in space? Second, if an electron is placed at r equals 2b, where does it move and why? If it is released from rest, what is its speed once it reaches r equals b? So we have the following strategy and sort of questions to guide us through this problem. The first thing is for any potential problem, we need to set a reference point, and we're going to go over how we pick this. You should sort of draw an analogy to when you took classical mechanics 1401. If you remember, in these problems, we would have like a ball of some distance h above the ground, and often we would set the ground to be potential energy equals 0, and wherever the height of the ball is to be mgh. But in principle, we could set the 0 point anywhere we want. So we just got to make sure we pick a smart point. Next, we actually need a strategy to compute what the potential is. If you remember maybe some other examples from recitation, one problem we did was a configuration of charges. In this case, we can just use this nice formula of V equals KQ over R and add them all together. But for Gauss's law type problems, we tend to integrate. So we'll show you how to set that up. And then for the last part of the problem, part B, we're basically going to use things that involve work energy and potential energy, kinetic energy. Since we're working with potentials, maybe using energy is sort of like a good hint. So what's first? How do we pick our reference point? We basically want to avoid having undefined quantities and infinities in our answer. So let's look at some examples. If the E field goes as 1 over r squared, 1 over r cubed, 1 over r to the fourth, etc., a good choice here would be r equals infinity. You'll notice that in these cases, these electric fields would tend to 0. Now, if the E field goes to 0 at, say, r equals 0, for a case like r squared, r cubed, and so on, we can choose a reference point to be equal r equals 0. But our problem here is a little bit different. We have the case of 1 over r. And we'll show you why, but a good choice for a lot of these problems is to pick the boundary of a conductor, or some value that you know. So let's start going through our potential reference points. We should first ask ourselves, does r equals 0 work? And the answer is no. Because if we look at E, as r goes to 0, because our electric field is basically some constant over r, E will go to infinity. And this is not good. So then our next case, I'm going to just tell you that r equals infinity also fails. This one might be a little harder to see just by looking at it. But the spoiler is that the integral of E dot ds, the integral we're going to end up doing, becomes a natural log. And the natural log as r goes to infinity is basically an infinity. So maybe our best bet is to use the boundary. So what I'm going to decide is to use r equals b. This is the boundary of the conductor. So with that out of the way, we now need a strategy for this. So because this is a Gauss's law problem, let's use our integral definition. V of r is equal to minus the integral of our reference point to our new point r of E dot ds. This is our go-to method for Gauss's law type problems. I'm going to grab a copy of this image of the problem real quick. Now, one question you might ask is sort of, what does this integral really mean? So if you've taken calculus 3 or 4, maybe you're familiar with line integrals, but just in case, We're deciding that we're setting our reference point to be here, or basically anywhere on this outer conductor's shell. In this case, we do the integral of E dot ds. We can think of ds. So maybe this is some distance here is r. ds is sort of this vector that connects us from, is a path connection. So this goes from the reference point to r. In this picture, this is basically the same as dr times r hat. So r hat is this radial vector that goes outward, and dr, you can think about it as like the length of this vector, some differential length. Now the electric field, I'm going to draw slightly to the side just for visuals. If you remember, it's also pointing in r hat. So what E dot ds is the dot product between the electric field and the path that we're taking. And you might notice we picked a situation of a lot of symmetry. If we actually compute this thing out, I'm going to write the electric field as like the component. So this might still be negative times r hat. We can rewrite this as E dr, r hat dot r hat. And this thing here is just 1. Two unit vectors dotted together, if they're exactly the same thing, is just 1. So this is what we mean by this line integral, or the dot product within the integral. So now that we have this settled, we can start solving this region by region. So the first region I want to look at is the case of r is greater than b. So maybe as a drawing, what we're looking at is, this is b. We're solving for some r maybe out here. So how do we do this? We first use our formula, v of r is equal to minus integral of the reference to r of E dot ds. I'm going to plug in our values. The reference is at b. So we're starting here and we're integrating out this way. It goes to some value r. And as we saw from the dot product above, this is basically going to be, I'm going to use r prime, E of r prime times d of r prime. I'm using prime here so that we don't get any confusion with r and r prime. It's just a dummy variable. From the problem statement, we know that this value is q plus q, big Q plus small q, 2 pi epsilon naught, r prime L, dr prime. Then all we need to do is compute this integral. So I'm going to pull out all the constants. And this integral here is the natural log. And just as a note, the natural log of r minus the natural log of b is equal to the natural log of r over b. So our final answer looks like this. So this is the potential just in the region of r is greater than b. So next, let's look at the region of a less than r less than b. We'll put the same figure off to the side. And what's happening here, I'm going to draw this like a sort of round trip picture. R would exist somewhere like here, but this is the point of B. So the path that we're taking is really like from this boundary B to the point R. So we'll call this thing R. In this case, we set up the same integral. Again, the reference point can't change. So we're going from B to R again. However, in this case, the electric field is really easy. We're just going to be integrating 0. And this is because we're inside a conductor, and we were also told in the problem that the electric field here is going to be 0. So with our reference point that we picked, we get the potential of 0 within the conductor. The final spacing we should look at is the case of r less than a. So we'll pull up the drawing again. And in this case, we're basically going from this edge inward to some value maybe here. So this would be our new r. We're going to set up the same integral. But what I'm going to do here is break it apart into two separate integrals. The first one will go from b to a, and then the second one will go from a to r. I'm doing this because our electric field that was given to us was a piecewise function. I'll note here that when a lot of students start learning about potentials, especially through the integral method, this is often the pitfall they fall for. You need to remember that your reference position can't be changing, and you should make sure that your integral for a piecewise function, like these bounds here, match. Maybe I'll use a different color to sort of highlight this. So all I've done here is basically split this up from a segment of b to a, and then a to r. Then when we do this integral, we first know that this term here is 0. How do we know that? Well, the electric field is 0 when it's between a, r, and b. So therefore, we only have to deal with this term. We take the same approach where we can evaluate the dot product. And now we just plug in what E is. So in this case, it was Q over 2 pi epsilon naught R. I'm going to use R prime again as a dummy variable, dr prime. Evaluating that gives us something very similar to the region before of a natural log. So therefore, our potential gives us minus Q over 2 pi epsilon naught L, natural log of R over A, for R less than A, 0 for the case of A is less than R is less than B, and minus Q plus Q over 2 pi epsilon naught L, natural log of R over B, for the case of R greater than B. And this would be our final answer. So with this, we can now move on to part B. This is the mechanical energy problem. So now the question is, we've placed an electron some distance 2b from the center. And we want to know what direction it's moving and why, and also find the velocity once it moves a distance b from the center, which is basically the edge of the conductor. So let's figure this out two ways. So if Q and Q are positive, we can sort of figure out that it will move inward, the minus r hat direction, because that points in. We could argue this via charges by saying like, well, if the charges are positive, then the electron should be attracted to it and therefore move in. But maybe a better argument is the following. So let's think about the energy. The potential energy we said is equal to Q times V. So in this case, it's negative E times V. If we then look at the signs of V, it turns out that closer to the conductor means lower potential energy. And this is generally how objects tend to move. So maybe sort of the cartoon example, if this is our potential energy curve, and we have a ball up here, if we push it, it's going to want to move down the hill. So with that, we can set up the problem. So using sort of our energy principles, we know that like energy initial, because there's no work being done, should be equal to energy final. Our initial energy, because it's at rest, has no kinetic energy, so we only have potential energy. And at the end, we could have both potential and kinetic energy. Let's maybe solve these one at a time. The initial potential energy is QV, or minus E times V. We're going to use V for the region of R greater than B, because we're outside of like we're even past the outmost shell. So we can plug in minus Q plus Q over 2 pi epsilon naught L, natural log of 2B over B. So normally the natural log here was R over B, but we know that the value of R here is 2B, because we're given that in the problem. So therefore, we simplify this a little bit, we're going to get EQ times Q plus Q, 2 pi epsilon naught L, natural log of 2. Our final potential energy can be found the same way. We're still going to be using the same one here, but you can also use the one for R is equal to R is less than B, because we'll actually find that for whatever value we plug in, we're going to get 0, because natural log of 1 is equal to 0. Finally, the kinetic energy should be equal to 1/2 mv squared, which then means if we set up our equation from up here, we should get EQ plus Q, or 2 pi epsilon naught L, natural log of 2, is equal to 0 plus 1/2 mv squared. And then from here, all it takes is some algebra to show that V is equal to the square root of EQ plus Q, where pi m epsilon naught L, natural log of 2. And that concludes this problem. So what are the main takeaways? For any potential problem, the first thing we need to make sure we know is how do we pick our reference point? There's a really good explanation that John has written up in his worksheet 5. But in this case, because we had like a 1 over R electric field, we picked the conductor. 2, how do we pick our strategy for calculating the potential? For Gauss's law type problems, we tend to use V equals minus integral of E dot ds. And then finally, part 3, our last takeaway should be to use the energy equations for solving velocities. Finally, I want to leave you with some variant problems you could look at. So with potentials, often they don't live as a standalone problem. They live as a part of a different problem. You can imagine that any problem you have in an electric field can also have potential, and it could also have some sort of work energy component to it. So what are some Gauss's law problems we might remember? Well, the first one is a ring of charge, or a disk of charge. What is the potential at some point P up here? What's another Gauss's law problem that we did? What about a bar of charge? 3 points we could consider. The one we did in recitation is the one right above the middle. You can do one off to the side. You could do one off, like sort of a line on the axis. What if we had 2 bars or multiple bars? What is the potential here? What is the potential here? Superposition also works in a lot of these cases, so you could sort of like add as many things as you want and complicate the electric field. The last Gauss's law case you might remember is that of the spherical shell. So you have a charged thing as in density rho. What is the potential out here? I have a note here to look at the worksheets 5 and 6, because other problems you can have is like configurations of charges. So one of them is, say I already have 3 charges placed. How much work does it take for me to place a 4th charge from infinity and bring it up to this point right here? You can think of another similar problem. What if I took another charge from infinity next to the bar of charge, some distance maybe r away? And then like part 3, you can do any sort of general problem of we have something that creates an electric field. What is the velocity of this particle going to be once it travels some distance r? And then maybe the last 2 things I'll bring up are parallel plates. So you'll learn about capacitors soon, but potential will show up there as well. And then also problems with like ground conductors. So this actually appears in worksheet number 6. So a lot of the potential problems are structured the same way. Hopefully you go through some of these examples and can see that a lot of the strategies you use, just making the right decisions, will easily get you to the answer.